Christian, and he will tell us how to probe the Planck scale with cosmic neutrinos.
Thank you, Subir, and thanks for inviting me here. My background is actually not in particle physics or quantum gravity or anything that you guys are experts on, but in foundations of quantum mechanics. But about 10 years ago, 15 years ago, I started to lose interest in foundations because I thought that it was becoming like the Tower of Babel. People were talking, but they were not listening to each other, and everybody was talking a different language. So I started to work a little bit on quantum gravity and did some work there. And to my horror, I discovered the situation is even worse. So what to do about that? And then a few years ago, I got into this neutrino business, got was fascinated by the physics of it, and realized that maybe a slightly different approach can be used to do some phenomenology with neutrinos and quantum gravity. And so my take on this is not moving.
Well, it moved earlier. Just press space.
Right. So my take on this is to think about this issue and make it less like a Tower of Babylon. So what I mean by that is that we look at it in a logical way, that without any prejudice for one approach or another approach of for quantum gravity. As we know, there are many different views and many different approaches. So the question is, what is logically possible? Well, there are four different logical, maybe many more possibilities. But at least four logically possible views seem to be kind of natural. The one is that we have two great theories, and both of them cannot possibly be right because we know that there are remarkable tensions between these two theories. So this particular logical possibility seems to be highly unlikely, but not impossible. It may be just that we haven't discovered the right way to match these two apparently incompatible theories. Another possibility is quantum mechanics is truly basic, and this seems to be the starting point of most people. And this possibility seems illogical, but it is not, in fact. And the person who supported this one, by the way, when I mean only GR, I mean the basic principles of GR, not literally the theory, naturally. Theory literally has its own limitations.
The basic principle, what do you mean?
Well, there is Lorentz invariance, equivalence principle, superposition principle, things like that. Right. So, for example, in GR you have a general covariance, and that is, from the GR point of view, that is the basic principle. When Einstein argued that one should preserve that, whatever the quantum theory says. Just a historical note, in 1916 he wrote a paper right after the GR paper, arguing that quantum effects must modify GR, his new theory of gravity. But the modification he seeked was in the form of generally covariant new theory. And that's why part of the reasons why he was not happy with quantum mechanics. That's another story. It seems to me that most likely possibility is that both of these theories, or both basic principles of both of these theories, are possibly both effective, not, and we have a completely new picture, and that seems to be the most logically possible. However, I'm not going to take sides. I'm just going to argue that maybe the cosmic neutrinos, and we have already heard about a few of those, so we already have the idea what cosmic neutrinos can do. And John Kelly gave a nice talk, but you're talking about high energy neutrinos. I'll be talking about ultra high energy neutrinos and extreme energy neutrinos. Because I have a theory, I can afford to do that. I don't have to do the hard work like you. Right. So what can we do? What can we test here? So basically, we come back to the things that we have heard about before: Lorentz invariance, equivalence principle, and superposition principle, and things like that. So how do we approach it? Now, people have been talking about neutrinos, but nobody has reviewed the theory. So maybe I will do it. So For those who know, this is boring. This is the elementary basic theory of how phenomenology of neutrinos is done. It is the part hand-waving, part rigorous phenomenological approach to neutrino physics. We know that the flavored neutrinos are a superposition of mass eigenstates, and the mass eigenstates of the neutrinos are superposition of flavor eigenstates, and they are related by the matrix, electronic mixing matrix like that. And we know that what happens, the neutrino flavor changes is no longer a speculation. We have seen this in various experiments about 10 years ago. So what happens is that the neutrinos produced at birth can oscillate to neutrino, different flavor of neutrino when they propagate to a large distance. And these flavor changes can be worked out. The transition probability in the standard quantum mechanical way can be worked out in a phenomenological way. Semi-theoretical way. And also it can be worked out using the rigorous quantum field theory, but I'm not going to do that. So the idea is to look at the plain wave solution of Schrodinger equation for a mass eigenstates of neutrinos, and then you approximate this to find out what is the momentum associated with the mass eigenstate of this neutrino, and this is using the dispersion relation, you can approximate this to be the energy of the neutrino in the lab frame, where the lab is at the source, and what you get is the relation between the momentum of the particular mass eigenstate of the neutrino and its mass and the energy of the neutrino in the lab frame. You can use this to then work out what the transition probability is. Transition probability, I mean transition from one flavor of the neutrino to the other flavor. So from this approximation, you can work out the solution of the plane wave can be approximated this one here, and then plug in to the superposition of the mass eigenstate for the flavor neutrinos, and then straightforward calculation, you can work out the transition probability, and if the neutrinos have mass or non-zero mass or non-degenerate, these masses are non-degenerate, then you get this extra factor, and that's what induces the flavor change. So for example, if the mass difference is 0, the masses are degenerate, or the masses are 0 for all of the flavors, then of course transition probability is just delta, and nothing happens, neutrinos remain the same. But we know by now that flavors do change. Neutrinos produced at the source do end up in a different flavor when they are detected at the detector. So that's the basic theory. Now, so from this transition probability, if you missed it, let's just, I keep going that way because I don't want to trip over this wire. But maybe I'll stay here. Right. Right. So if you miss this, this is the factor. This is the oscillating factor, and it depends on the phase factor. And so you can define the oscillation length by 4 pi e over delta m. Delta m is the mass difference between two different flavors of neutrino. Sorry, two different masses within the superposition of neutrino flavor. And this is the propagation distance, is how far neutrino is traveling the lab frame situated at the source. So, for phenomenology, one can only concentrate on these two and get away with it, and that's what we're going to do. Right. So, I mentioned 3 different principles. Basically, that's what I'm going to think about, and one is the equivalence principle, and the question is what modification of this oscillation length occurs if the principle of equivalence is compromised in some way. And let me remind you that I'm not going to look at the cosmic neutrinos, so I'm very ambitious and I want to look at suppression by several orders of magnitude of Planck mass, not just one or two. That's
when you talk about principle of equivalence, you mean which one?
The weak equivalence.
Sorry, the weak.
So neutrinos are falling in a static gravitational field.
The strong you do nothing about.
Even I am not that ambitious. So, actually, I have some ideas, but I'm not going to talk about them. Right. So the trick is to, Nikos already mentioned some of this, that you start with the linearized theory, flat metric, and then you say that this moves slowly, gravitational pressure is static or moves slowly compared to the other terms in, say, direct Lagrangian, interaction Lagrangian for the neutrino mass. And so under that approximation, you get a very simple equation of motion from this Lagrangian, and you can use the ppn parameter for it to relate h mu nu to the static gravitational field of a source. For example,
your violation of the equivalence principle is in the alpha j's. If all they were
that's
the same,
right. That Toppling constant, which
if they were the same, you would have normal stuff.
That's right. Right. So this J means mass. So mass 1, mass 1. Right. So gamma, the ppn parameter is the dimensionless parameter, whereas alpha is the gravitational coupling. So that ratio between the gravitational coupling defined by that and the neutrino mass of it. Right. You might wonder, what am I doing different, apart from what I already think that I already said, from what has been talked about already? Well, I want to see what qualitative difference these three principles, violation of these three principles can induce on the same specific physical phenomena, namely neutrino oscillation. So that's one of the aims. So equivalence principle induces this kind of change. Let me go through what change is occurring. Did you start file pass?
No, a few minutes first.
So what happens under this change in the what we talked about, the change we talked about then leads to the change in the dispersion relation, and that can then lead to the change in the oscillation, so momenta of the neutrino masses, and that can then lead to the change in the oscillation length, which is on the next slide. There. So oscillation length was, remember, 4 pi over delta m square, but this extra factor with this dimensional parameter which depends on the mass induces a change, and to observe this.
That energy is energy as measured
In the lab.
with respect to which metric? The original
The
flat
flat
metric?
metric.
So you are ignoring the fact that in the lab we also have the influence on all the substances
Yeah.
of the gravitational
Well,
correction.
assumption here is that those influences are negligible. Because there are various approximations which are wrong, a lot more than what you just mentioned. Right. So then if these two factors are of the same order, then we should be able to see something. Okay? And already, right, so then one can find out the sensitivity of this by working out what delta gamma is. And notice that delta gamma is actually inversely proportional to the propagation distance and the energy of the neutrino. So larger than, and that's why I'm looking for cosmic neutrinos, because the larger the base length, and the larger the energy of the neutrinos, we can get a very sensitive probe. And already with solar neutrinos, you can work out that the equivalence principle is bounded by a very strong bound, violation of equivalence principle. Imagine now that if the neutrinos are coming from very far away, then this bound will be much, much stronger. Okay? Next, one can look for the violations of Lorentz invariance with the same sort of change in the dispersion relation, but this time parameterized to all orders of n, all orders of, so suppression by all orders of Planck mass. And we want to find out how far we can push this, what and we can reasonably hope to see in the neutrino oscillation experiment using cosmic neutrinos. So you can expand it to the second order just to see what happens. And again, the change is in the oscillation length, and you have this extra factor coming in. And if these two factors are the same order, then we should be able to see something. That's the idea. Right. So then one can work out, for more generic situation, this delta gamma, so delta c are again dimensionless parameters in the expansion of the dispersion relation modified by Planck length, and one can work out what happens for a generic such change. The logic is the same as the inequivalence principle. So you have the similar order, same order of magnitude change in the oscillation length, and you want to work out what or how far we can push these.
But again, it has to be differential. Different dispersion relations for different species of neutrinos. But
okay. So, question then is how sensitive, what kind of sensitivity in this kind of probe one can achieve, and notice that the energy and the length of the neutrinos are in the denominator. That means they are inversely proportional. The sensitivity is inversely proportional to the propagation distance and the energy, but not just the energy, it's the powers of energy, n plus 1 power of energy, where n is the power of the Planck mass suppression for this particular situation. And we can have a theoretically remarkable results. For example, for n equal to 2, which is the second order of suppression by Planck mass, we can have a remarkable ridge and remarkable sensitivity, 10 to the minus 24. But even if the suppression by 7 order of magnitude of Planck mass can lead you to some sort of detectability or violation, which is quite easy to see from this looking formula.
Observationally, how would I cast such a constraint combination? Say we can have this sensitivity up to 10 to the minus 24, but basically you should understand that you're using the neutrino oscillation, so you should be knowing what is started from the source. I don't understand exactly what kind of observation you would use to test this.
Oh yes, what one looks normally is the ratios of different fluxes coming towards us. So we have models of cosmic, so for example, AGN and GRBs, the active galactic nuclei and GRB nuclei, where there's something called a standard ratio, which is the ratio of electron neutrino, muon neutrino, and tau neutrino, which is 1, 2, and 0. I'll come to that in a second.
Okay.
Yeah. And then what you detect is different. But the question is, how different? And for each violation, it is qualitatively different. That is the point that I'm saying. Qualitatively different. And I'll tell you what I mean by that. Okay.
So it seems to me you need to compare two experiments. One from which you extract the difference in masses, and another experiment on which you test your result. But you have only one experiment.
No, I'll show you.
Okay.
Right. So, third one is the superposition principle. Now, Nick mentioned that you have the decoherence effect. Well, I'm talking about fundamental decay in the superposition, right? Okay. Very different from just the decoherence effect. Again, there is a qualitative difference between just pure decoherence and fundamental breakdown of superposition principle. Now, what does the breakdown mean? We have a specific mechanism of various sorts. One is called the GRW mechanism and so on and so forth. The one that I prefer for this analysis is Roger Penrose's idea, where he specifically has idea of decay or superposition for different masses. And that's attractive for us because neutrinos have masses, and that's what I'm trying to do. I'm trying to see what the difference in mass can be. So, okay, I don't think I have time to go through this because I want to address the questions that you raised, which is much more important. But the point here is that this kind of decay again leads to the change in the oscillation length, and this change is, there's a lot which goes into this reasoning which I'm not going to go through. But what I want to point out is that again the transition probability of flavor from one flavor to other induces a change in the oscillation length, and that change comes from the change in the transition probability. And notice that this is the damping factor that Nick also mentioned, but that's a different damping factor you mentioned. Here it comes a very specific damping factor. So in fact, if you know about Roger Penrose's idea, it's very difficult to rule that idea out with any experiment that we know on Earth. But this one, you can rule it out. So that's an advantage. I'll show you the numbers if you want to see later how you can rule it out. So now I come to the question of observability and how your question is, how is it different?
Can I ask, is your breakdown of superposition principle, is it related to quantum gravity, or it could be due to some...
Oh, it could be anything.
It could be anything. So I'm only doing it in flash space-time, and you just assume that...
So I'm sure you know the Rogers idea. And Dioschi was the first before Roger who did that. And the idea is that it's just an answer.
Yeah.
Irrelevant of whatever other thing is. And his motivation is coming from quantum gravity, but also from foundations of quantum mechanics. So, right. So these are some numbers and what kind of bound you can put on Roger's, Penrose and Dioschi's idea. And not bad. 10 to the minus 3 suppression is actually pretty good because if you can show this, that means that idea is pretty much dead because this is 1,000 times smaller than what they need to work their idea out. Okay, so now I hope this is related to your question. The question is, we have, what I talked about is the breakdown of 3 different principles, say equivalence principle, Lorentz invariance, position principle. But you can have a standard theory, right? So you have, so you expect that, normally you would expect this transition probability, therefore you know what kind of flux you're going to see if quantum theory and everything else is correct. So suppose you have, for example, we do have models in which you have a standard ratios coming from specific sources like AGN or GRV. I'm not going to talk about how reliable they are, but they are called standard because they are kind of reliable. And so what you receive at the detector is a ratio which you can expect from the standard theory. But this standard theory is modified in qualitatively different way if these 3 principles are modified. So suppose, I mean, optimistically, suppose only one of them is compromised in some way. Then, just by looking at the ratio coming from various different sources and making a whole spectrum of observations, we could detect that which principle is actually being compromised. Looking at the, you're not happy, John, but we just, you're okay. No, but I want your input more. Now, does that address your question? Or?
Yeah, well, yes, you're answering part of my question. My question was, in some sense, its applicability given the fact, given the data that we have today. My point is the following, that I could take for example, your third example, and call all these and look at the coefficient of L there. This whole coefficient, I could call it my effective delta MJK. That whole thing is an effective delta. So in order to distinguish the first and the third, I have to have several experiments to log on to the different energy dependencies.
So-
Measuring things at one energy, for example, to extract the delta NJ case, and then measure it at another energy to be able to extract the second coefficient.
Yes, you're
if
right.
not, I cannot
I
disentangle.
agree. I agree. That, I mean, for example, you need to know the masses precisely. Suppose you have an experiment in which you actually determine masses for that source, and then you can be sure that we know its masses are there and so on. So, I'm a theorist, you see.
No. Okay, I thought it.
Okay, but I take your point. And you happy?
I'm happy.
No, I mean, you also had something similar.
Actually, I was close to you.
I mean, we know what delta M squared is, for example, in the atmospheric Rings acceptors. So because these effects have different energy signature,
Okay.
for example,
But I thought
if
it-
you work in an energy regime where you don't have any more atmospheric neutrino oscillations, for example, then
I'm not an expert, but I thought the flavor species involved in one and the flavor species involved in the other are different. So
there they could be, and then it's more complicated.
Well, there are, I mean, now that you mention, there are various things that I haven't mentioned. That is the sterile nuclear, for example. I've just only done the 3 flavors, so there are other issues. But what I want to, I mean, my goal here is to show that there are qualitative differences coming from these 3 principles, and the suppression up to 7-fold of plant mass can, in principle, be tested. I think that it itself makes it interesting. So. But of course, there are issues. Right?
yeah.
Okay. Your computer is not fully protected. So.
Close.
I don't know.
Is this, no, is this? I think it's this thing. No.
No.
No, this is something else. Well, I won't get into that. Right. So this is the difference in ratio that I mentioned. So this particular ratio is called the standard ratio coming from the cosmic sources, and John knows probably more about these than I. But they are called standard ratio for a reason. I mean, they are pretty much believed in by many people. So we know that if we receive the ratios on Earth, which is different, then how different it is. Standard theory predicts one thing. If one of these principles are violated, then each one predicts different ratio. So already we know we can't be for certain for sure, but we have an indication that which particular principle is compromised. That's progress. Okay. I'm supposed to stop now, according to Sabine's indication. So there.
So the parameter of the superposition principle, there must be bounds in it, probably very strong bounds.
Well, not very strong, unfortunately, because if you Penrose is a clever guy. So the model they have proposed is pretty. I mean, I tell you how incredible it is. You would think that any violation of the superposition principle should be detected, but so these kind of decay that Diosyn Penrose proposes is that for the nucleon, say for example, any nucleon, proton for example, delta R, the mean life, see this mean life is 10 to the 7 years. So for all practical purposes, you will never see the decay. But just change that to a speck of dust, a tiny speck of dust, and it plunges to minus 13 seconds. Look at the difference in that. So it's not so easy to detect this decay of superposition. However, cosmic neutrino has its own advantage. And in that, I am able to put a bound this much. But if you know that scheme, that's strong enough. So that is 1,000 times smaller the effect have to be 1,000 times stronger than what Penrose and Yoshi predict. Otherwise, they're useless.
But where do you get a lower? Where do they get a lower bound? I mean, of course, for the neutrons, you want them to be, to stay as long as possible. But why do I have to have the collapse of that soon for the speck of dust? Perhaps it takes.
Well, that's right. Well, that's perfectly compatible with the reasoning comes from foundations of quantum mechanics.
You need to have data you want to explain.
Well, yes. So for the kind of model they have proposed, this collapse for the speck of dust is perfectly compatible with everything we have seen in lab.
But if it's
yes,
1,000 times slower, it's also compatible.
No, this is a bound on their parameter. That parameter is order 1. So they have to have this parameter in their model of order 1 for their model to work. Where is it? Yeah, this one here. And I'm putting a bound on this dimensionless parameter.
What I understand is what does it mean for the model to work? If it's 1,000 times smaller, why doesn't it work?
If it doesn't, because it violates immediately what we have already seen in the lab. Right? So it's up, model's up. So if this one is 1,000 times smaller, then it's incompatible with what we already know from the everyday experiments in quantum mechanics. Yes?
What do you do in neutral chaos? In neutral chaos, K0, K0 bar oscillations, have you...
No, I haven't worked it
You
out.
haven't-
You mean the Rogers idea?
No, if the breakdown of superposition principle occurs, it would affect the chaos.
That's right. Yeah, I haven't
So you
worked it out.
done
But it's a good question. Yeah. Right.
Just a comment, I think independently there is a guy from Santa Barbara who is working really hard on falsifying.
Yes, I know. What's his name?
No,
Baumeister. Okay, that's a completely different. Okay, that's a good point. Let me address that. It's a completely different experiment. What they're trying to do is make a superposition of a little mirror, a macroscopic mirror. Now, what's the problem with that? Well, decoherence is a problem. How are you going to cool down the system to such an extent that the effect that you see is not due to everyday decoherence rather than actual effect? The advantage here is the neutrinos are neutral to any electromagnetic decoherence. So, yeah. So,
First a comment. I'm regarding your separation between violations of the equivalence principle and the Lorentz violation. I'm not sure it's quite as clear cut as that because, for example, the first model that I showed where you just have this single delta CFC split in neutrino flavors, that actually gives you the exact same survival probability equations as the violation of the equivalence principle, which in a sense is good for you, right? Because you can take limits on one and immediately port them to the other. So I think that improves your limits on violation of the equivalence principle, at least as Gasparini taught.
yes, yes. So yes and no. I mean, I'm agreeing with you, and also I'm going to show you that it's not
exactly the same.
because it's not. You see, here the energy dependence is linear. I mean, so
Yes, but you just
it's
left
first
out
order.
that term in the
Right. So in that case, you can do that.
Yes.
But what about all sorts of orders? You can check various orders of
Yes.
suppression of Planck mass, and then you can tell because there is no such suppressions here. So
Experimentally, it's hard to disentangle when it's at the end of your spectrum.
Right.
You've also set limits on higher order
that's right.
energy.
Up to seventh order, you can actually do calculations.
Actually, if I may add on this point, it's exactly your point. There was a discussion at the start of quantum gravity phenomenology, in a sense, around the year 2000, exactly about the fact if in violating Lorentz invariance, we should put the same coefficient, where initially most of the dispersion relation has the same coefficient for all the particles. And one argument was to not violate somehow the equivalence principle, and it was shown by David Martin that basically when you have a modified dispersion relation, that implies also violation of the weak equivalence principle. While of course it's not obvious the contrary. I mean, you may have probably that you may have a way of violating the weak equivalence principle without doing anything bad to local Lorentz invariances. As in fact, this is coming as another assumption when you want to motivate the Einstein equivalence principle.
In some sense, they are logically very tightly connected, the equivalence principle and Lorentz invariance. So in some sense, it's kind of surprising you one can disentangle.
Well, I'm not saying that you completely disentangle it. This is just I would take it as just an indication. You look at various orders of suppression, and suppose you see something where something is happening in your oscillations, but sorry, let me phrase it again. Because of the difference in this suppression scenario, here you have just no effect of the change of order of suppression, as here there is. So you can, I can't think of how, but you can make an inference. I don't know, maybe I'm not clear, not answering your question for you. Yeah.
Just one more question, if I may. You mentioned at the end about the 1 to 2 to 0 predicted flavor ratios, neutrino flavor ratios at astrophysical sources. Now, this will...
No, cosmological sources.
Sorry?
Cosmological sources. Cosmologically distant sources.
Right. Like
Not
GN or whatever. Yeah. Sorry, same thing.
Yeah.
Now this, because of just conventional mass-induced oscillations, this will end up for large L at 1 to 1 to 1
No.
for us.
Right. Good.
So I'm wondering if have you sort of gone through specific scenarios?
Yes.
Because it
Yes.
could be that in many of these cases, if L is too large, then they look the same.
No, this is a fundamentally different analysis. So, for example, the thing you mentioned, the propagation distance is so large that the phases are oscillating so fast that any ratio whatsoever is going to end up 1, 1, 1. This is something we talked about earlier as well. This is different here. The very fact that I'm comparing the denominator of the oscillation length, which shows you that what I'm comparing requires the oscillation length of the same order as the propagation distance in all of these cases. So that decoherence effect doesn't occur here. It is important. Let me show you how this is done. Tell me when to stop. I don't know.
Yeah, you have 5 minutes.
Right, here. This is the observability condition, right? And the way I have derived conditions like these requires that oscillation length and the propagation distance of the same order. So that very logic of the decoherence does not affect this analysis. Okay, so it's done differently.
Okay, so if there's no more questions, then let's thank Troy again.